an honor to have Professor Warren Powell. Professor Powell did his PhD in 1981 from MIT and has started his career at Princeton ever since. And he recently had become Professor Emeritus, as well as the Chief Analytics Officer of Optimal Dynamics. Very exciting new venture. His work has spanned over a wide range of topics, both on the theoretical side as well as domain application side. So in the spirit of keeping the introduction brief, and we would let Professor Warren Powell take it over. And we very much look forward to your webinar. Thank you.
Thank you so much. I really appreciate the invitation. I cannot hide my enthusiasm. It took me a career to figure out the material that I'm going to be showing you. And it was all application driven, but also spent a lot of time working in the various academic environments. Let me start off. Okay. So I'm going to give sort of overview some various applications. By the way, beginning with laboratory science, I spent 5 years on a AFOSR project on material science. So we built algorithms for a robotic scientist where the decision was what experiment to run next. You can go all the way up to ride-hailing fleets, where one decision is when a customer calls in, which car do you choose? But now they use a very simple logic for that. But another decision is what price to charge. Now, this was really the complicated problem, because you can easily have periods of time when you have way too many riders or way too many drivers, and that's just really bad for the company. So what they do is they tweak the price to try to keep the two in balance. The problem is what they have to do is try out different prices, and the decision is what price to charge. And then they have to try to learn the response of both the riders that don't like a high price, but also the drivers that do not like a low price. This is the problem that started my career in 1981. I learned about truckload trucking. This is Uber for trucks. So just like Uber, you have a rider and you have to pick the car that takes the car from A to B. This is where you have a load of freight, where the load fills up the whole truck and the truck has to take the freight from A to B. It's just the difference is that A and B are much farther apart, usually many hundreds of miles, and a lot of uncertainty because of the last minute demands, and you're modeling a much larger and harder problem. It took us a surprising number of years, I'm going to say close to 20 years, to figure out the algorithms where we could optimize the assignment of drivers to loads, picking out which loads to move, getting drivers home, all the complicated operational details. Energy is a fabulous area of decisions with uncertainty. You've got to make decisions about scheduling nuclear power plants and gas turbines and steam turbines, and you have to deal with the vagaries of wind and solar. With wind, this is a year's worth of wind. You can see there's seasonal variations, there's daily variations, there's hourly variations, a lot of uncertainty you have to deal with. Another problem is drone sensing. This is where we have to send a drone out over the ocean and try to sense places where you have concentrations of spillage. And then you have the physical vehicles that go to clean up the spill. So you have a sensing problem, information collection, communication, and then a mitigation where you actually have the physical resources. We've also done some large supply chain problems. Very hot topic today. You see it all through the newspapers. These are multi-agent problems. You've got many decision makers and endless source of uncertainties. This is kind of a one-screen snapshot of many of the problems I've personally worked on. Trucking problems, manufacturing problems, warehousing, logistics, supply chain, health, energy, e-commerce, and finance. The world of human processes is the world of sequential decisions. Every one of these fields, and each one of these are big. Like I just have one box called engineering. I mean, so that covers an awful lot. Another one called freight transportation, another one called business processes. And in all of these, you have people making decisions while new information is coming in. Now, what we want to do is do a better job of running these systems. And for that, we want to achieve various goals and objectives. And by the way, you can sometimes come up with many dozens of goals and objectives, reducing cost or increasing profits. Maybe I just want to improve health or reduce risk. Maybe I want to maximize employee retention or minimize lives lost. There's no shortage of goals and objectives. How do I do better? The way you do better is by making decisions. Now, this is going to come as a surprise. There's a lot of big problems, especially the more complex problems, where simply identifying what decisions have to be made is not always obvious. Like if you want to reduce carbon in the atmosphere, what decisions do you make? Well, you have to sit and think about it. What if you want to do a better job running your supply chain? What if you want to respond to the COVID pandemic better? What decisions are out there? Simply listing them is a challenge. I mean, I love to go to people in supply chain management, say, what decisions do you make? Every time I get a blank stare. Now, once you've identified the decisions, which is not always a small task, now we have to say, how do we make better decisions? And somewhere somebody's going to raise their hand and say, we need artificial intelligence. So there's a lot of confusion about artificial intelligence. In the 1960s and 70s, it was rule-based. If eating meat, drink red wine, or if the patient has certain characteristics, use the following treatment. In the 1990s, it was optimization. It was this big flurry when CPLEX in the beginning suddenly could solve very large-scale problems, and big supply chains were saying, let's optimize the whole supply chain. Early 2000s, machine learning became the new AI, and this is where neural networks emerged to do voice recognition and pattern recognition. And that was truly a breakthrough. I mean, there's absolutely no question that neural networks work for these problem classes. They don't work for as many problem classes as people think. And so there's a lot of people out there saying, oh, let's solve it with the neural network. I'm like, calm down. It doesn't work for everything. I'll give you some examples why. But let's think about the 2020s. What's next? What I'm going to do is I'm going to claim that what's next is sequential decision problems. This is where we need to make decisions over time as new information arrives. This is not a new problem. There's 15 distinct fields with a variety of different vocabularies that all work on sequential decision problems, all speaking different vocabularies. One of which is called reinforcement learning, which has attracted a tremendous amount of attention. But it turns out reinforcement learning is just one of the fields. It's just a field that attracted an enormous amount of attention. I'm going to actually give you a picture that I think the umbrella I'm about to paint is broader than what I've seen in the reinforcement learning community. So everything that I'm going to describe falls in reinforcement learning, but I'm going to give you a little bigger view of it. So I'm going to start off with a series of topics, beginning with a quick overview of what I call the 5 layers of intelligence. So at the top of the 5 layers of intelligence is decisions. That's where I want to get. But you really do have to start at the bottom, if information acquisition and storage. What is the state of the world? It turns out this is a really big deal. Like, what's the level of carbon in the atmosphere? Where is my product? What's the efficacy of this new vaccine? Knowing the state of the world is very hard. Then you have to communicate, and then you have to do what we call basic transactions execution. In supply chains, these would be ERP systems, and trucking companies would use transportation management systems, and you get the rooms full of computers with a lot of people talking. So what I want to do is move quickly to that 4th layer, learning. Okay, so right now there's a lot of people who you say AI, and they think you mean learning. So let's take a quick peek. There's 4 types of learning problems. Pattern matching, is that a flower? Classification, hey, what product should I recommend for the customer? What ad or what news clip should I put up on the website? Inference, how is the market going to respond to a change in price? Or what's the condition of a piece of equipment? This is where you're trying to estimate something you just don't know or can't know perfectly. And of course, there's good old-fashioned prediction. Here's the history of what's going to happen in the future. Now, anytime you do machine learning, you're going to be working with 3 types of functions: lookup tables, parametric models, non-parametric models. Now, these are overlapping classes. I can give you a lookup table and wave my hands, and suddenly I can show that I can write it down as a parametric model. You might ask, where's neural networks? It turns out, okay, it's in there. Neural networks sort of sit between parametric models, which basically describe the shallow neural networks, or deep neural networks, which is technically a non-parametric model. And it took me a number of years to get my statistics colleagues to really sort that out. But whatever it is, we've got these 3 broad classes of functions. Anytime anybody does anything with machine learning, they're basically fitting one of these 3 broad classes of functions. And the non-parametrics, like the deep neural networks, are the most flexible, but they also require huge data sets. So there's a give and take there. So here's a machine learning problem where I've got to find the best function. So that F is some statistical model. Now, let's imagine that I'm trying to predict demand as a function of price. So I got some data points and somebody comes running in and says, I think it's a linear function. I actually work with a revenue management person who thought this. Well, of course, you want to come up with the best linear fit. But somebody else may come in and go, oh, no, it's not linear. You need some sort of a logistic regression to capture the nonlinear response. And trust me, you put this out today and somebody's going to come in and say, you got to use a neural network. But as I'm going to show you in just a moment, neural networks are very vulnerable to overfitting. Now, whatever you're going to do, you're going to pick from one of these three circles. And so what you have to do is search over. So F there is what class of function, and the thetas are the tunable parameters. That's where you pick the best within a class. And usually picking the F is sort of ad hoc, somebody with a lot of experience. I mean, by the way, this is one of the reasons why neural networks are so popular, because they can fit almost anything. So then I don't have to pick a function. But now, of course, you need a big data set in order to fit that function. So this is the requirement of doing machine learning, specifically supervised learning. So here's a simple called a news vendor problem where I have to order a quantity of product from which I'm going to then observe a demand. The demand might be high or might be low. And then from this, I have to estimate the profit function. And if I take all that noisy data and fit it with a neural network, I'm going to get that loopy curve. The real curve is that red function. And I may not know where the red function is, but I can tell you it's smooth. And I can tell you it's concave. This is what neural networks really struggle at. If you had trying to fit a function that has structure, but you have to fit it with noise, you're going to have a rough time. Here's one of our logistic curve. Demand is a function of price. The red dots are either I did buy it or I didn't buy it. And the green is the neural network fit, and you get something loopy because if you go in there with a big neural network, it's going to fit noise. So everybody, please watch out when you go running to neural networks. Now, the fun part, decisions. This is where we get to humans making decisions. Now, there's a lot of problems where humans making decisions looks like one of these rooms full of people and computers and a lot of people making decisions at the computers. Now, what I think is, so we're all familiar in engineering with the move toward robotics. I think that those rooms full of people making decisions, what we aspire to do is to get to things like Tesla's factory, where it's very high percentage of robots making decisions. And we need to teach computers how to make these decisions. So if we take my screen of all my various favorite application areas, behind each one of these problems is a set of decisions. Now, a decision is where I have a choice, which means I have good choices and bad choices. And I want to make the good choices that work well, but it has to work well in a dynamic environment where new information is coming in. So just as we could divide machine learning into these various classes, decisions, the same thing. We have decisions that act on physical resources, managing inventories, moving trucks and drivers and machines, scheduling nurses or energy generators. We have financial decisions of moving money around, pricing decisions, insurance contracts. And then finally, we have information decisions where I make decisions to move information, marketing decisions, running an experiment in the lab or in the field, like a market test. These are all decisions to collect information. And then, of course, I have the issue of sharing information. Now, you have to deal with the different time frames. Strategic planning decisions could be how many gas turbines should the power grid have? How do you design a building to withstand earthquakes? And what should the capacity of a reservoir be? Tactical planning decisions are the decisions where a decision now impacts the future, but it depends on the state of the system now. How much energy generation should we plan in the grid for tomorrow? How many gallons of water should be ordered in anticipation of a hurricane that's coming in? So these are decisions for the future, but reacting to real-time events. And then we have the real-time events of managing ramping decisions for energy, assigning a driver to load, or figuring out which doctor should handle a patient or what medical treatment. And so we have the strategic decisions, which are off in the future. They don't depend on the state of the system now. We have the tactical decisions. We're making a decision that impacts the future, but it does depend on the state of the system now. And the real-time decision to act on the state of the system now, but then we have to think about decisions in the future which capture the downstream impact of a decision made now. Now, we have this language of optimization, and one of the beautiful things about this language is it's spoken around the world. So, I'll say roughly invented by George Danzig. It actually predates George Danzig, but he was the one who made it famous because he came up with a way of solving these problems. And if you go get somebody who has some training or a degree in optimization, and it doesn't matter from which country, they will understand this math, and then they can go into complicated, messy problems like an airline. This became very popular in the 1990s. And they understand how to translate that physical problem into this math, at which point you have packages that will output an airline schedule. So this is an established field. There's established packages, and you can hire people, and CEOs can go out and build up a staff of these people. Similar things with machine learning. We have simple deterministic optimization problems like finding the best path. We can have higher dimensional problems like how do I locate all of my facilities? Sequential decisions don't look like that. They have decision followed by information, followed by more decisions, more information, and so on and so forth. These are sequential decision problems. Now, with sequential decision problems, maybe I have an inventory problem where I make a decision to order inventory now that might arrive now, or maybe it arrives at some point in the future. If it comes in from China, it might take 3 months. After that is when I observe the demands. And then I have another decision which can arrive in the future. Then I observe more demands, and so on and so forth. So this is the sequencing of demands and information. Dispatching trucks, I have drivers and loads. I have to assign drivers to loads. And as the drivers and loads are assigned each other, more loads are being called in, drivers are late, sometimes they quit, prices are moving around. Testing out new vaccines. I'm going to be running various tests in a clinical trial, observing how people respond to the different vaccines, or actually administering the vaccines and watching how the population responds. And maybe you're working on Wall Street. Let's face it, at the end of the day, everything's a sequential decision problem with uncertainty, certainly in Wall Street. Now, when you take a look at all my pet problems, so just think of this as a whole wide range of applications. Behind every one of these is a decision. Every time I make a decision, information arrives. So this is information that arrived after I made the decision that was relevant to how well the decision would work out. And so this is very rich, understanding this information that's coming, that and maybe I know about the information, I just don't know what it's going to be. I don't know how many drivers or shippers, or I don't know what the price changes can be. I don't know how the patient is going to respond. This is new information arriving. Now, if I take a really trivial problem, buy, sell, or hold an asset. So you take what you know now, make this buy, sell, or hold decision, then the price goes up, down, or stays the same. And then I make another buy, sell, or hold decision, and so on and so forth. And here you have the tree, and it just explodes. And this is a trivial problem. I only have 3 possible decisions and 3 possible outcomes. So let's talk about how to model sequential decision problems. So the biggest challenge of any problem when you put it on the computer is you have to write it down mathematically. Now, if you happen to be working on a deterministic optimization problem or a machine learning problem, everybody with training in math programming or machine learning, they know how to write down their problem. There's standard ways everybody knows how to do it. Not with sequential decision problems. Sequential decision problems, it's a complete mess. I've been calling this for many years the jungle of stochastic optimization. Every one of these terms is a distinct field. There's books behind every one, sometimes a whole series of books like Optimal Control. There's about 8 different languages and then various dialects. They all have different techniques. They all have different motivating applications. There is some overlap because I can take the technique one and apply it to another, but often not. Quite often the techniques have evolved in response to certain classes of applications. So let me just show you how to model a sequential decision problem. You have state at time t. This is the state of what you know. This is the state of knowledge, okay? Then you make a decision what to do. X can be a scalar or a vector. Then here's all the new information that arises that then takes me to my next state. Every time I make a decision, I get a cost or contribution. Decisions are made with a method that we're going to call a policy. And there's a lot of words for that I'll show you later. But what we're going to do is we need to pick a method and find the method that works the best. I can break down any sequential decision problem into 5 elements: state variables, decision variables. Decisions, of course, are made with a policy that I have to then design, but we're going to do that later. One of the mistakes made in all these books is they've already picked the policy. It's like a hammer looking for a nail. The transition function talks about how, given a state and a decision, then you take the new information. These are the equations that take you to the new state. And finally, you have an objective function that says, what's the best policy? Okay. These 5 elements describe all of the 15 fields, every single problem. Okay. There's tweaks to the objective function, and modeling is a very interesting process, but this covers everything. Now, the way I like to work on problems, I like to start on asking, often, what are the performance metrics? What are you trying to achieve? Then what decisions are involved? Now, sometimes this is trivial and sometimes it's not obvious at all. Sometimes you need to sit down with a whiteboard and have a chat. And finding all the decisions, say, to cure the opioid crisis or deal with the pandemic or solve the climate change problem, finding the list of decisions is not trivial. But it's nowhere near as hard as identifying the sources of uncertainty. Okay, so we have new information coming in, but it's not always obvious what the new information is. That's I tell people, get a 6-pack of beer and a whiteboard and just brainstorm. And then finally, there's this thing called the state variable. Over time, while building the model, is how you build the state variable. The state variable is what tells you what you need to know. Now, there's going to be some stuff that's not knowable, so you represent that with a probability distribution. That's fine, okay? But whatever, it's what you know and how well you know it. Now, let's talk about how to design policies, okay? So the real challenge here is fine, and all that uncertainty stuff, that is hard. But let's talk about designing policies. And what I'm going to be doing is describing 4 classes of policies. And I'm going to claim that these 4 classes cover any method for making a decision. So I often get people asking me, what do I mean by a policy? A policy is a method that maps a state variable into a decision. Any method. I don't care what method you have. A lot of people equate the word policy with certain types of methods. That's just wrong. Just think of it as a method as a black box. You pass in the state variable, it passes you back an answer. I don't care what happened inside the black box. Now, it turns out I have found that in the English language, there's about 45 different words. A friend of mine from Brazil translated this into Portuguese. I have a spreadsheet on the internet. If anybody would like to translate this to, I don't know, some other, whatever your home language is, let me know. I can set up a tab for you and you can translate all this into your language. So let's talk about how to design a policy. Policies, it turns out, come in a small number of classes. Now, the first thing that we're going to have to do is figure out how to evaluate a policy. So there's 3 rough ways of evaluating a policy. One is the mathematicians love to come in. Either they have an optimality of proof or regret bound or asymptotic convergence. The theoreticians love to go to town proving that this policy or class of policy works this well. Much more often, we're writing simulators to say, okay, let's test out the policy inside a simulator. Now, we don't always have a numerical simulator. Sometimes we have a physical lab, and sometimes we have to do this in the real world. We actually have to just put it in the field and see how well it works. Now, I like to compare machine learning to sequential decisions. Let's remind ourselves, with machine learning, I have to pick a function. We call it a statistical model. I have to pick a class of model, and I want to find the best within the class. Sequential decisions, I have to pick a function, but we call it a policy. It's a method for making decisions. It's still a function. With machine learning, I have to have a big data set to fit my model to the data. And with sequential decisions, I do not need a big data set. I need a model. I need a cost or contribution function, especially I need that transition function in a model of the uncertainty. So let's talk about how do I search over policies. There are two fundamental strategies for creating policies. One I call the policy search class. This is where you search over functions that work well over time. And the Lookahead class that says, I'm going to build a policy by maximizing the contribution of an immediate decision plus downstream rewards, okay? So each of these I will further divide into two more classes to give us our 4 classes of policies. Let's start with policy search. The first of the 2 policy search classes I call policy function approximations. This is some sort of analytic function that maps a state to an action. So inventory theory, order up to. If the inventory goes below one number, order up to another number, simple rule. In Wall Street, buy low, sell high, okay? But it could be any lookup table. Doctors often work with PFAs. Oh, this type of patient has these characteristics, so therefore there is this treatment. It could be a linear, nonlinear model. It could be a neural network, and there's a lot of people get excited about using neural networks. You can train a neural network to work well over time. So the second class I call cost function approximations. Now, PFAs you're going to see in the literature. CFAs, believe it or not, you're not going to see this much in the academic literature, widely used in practice. This is what people do in the real world. They take a simplified optimization problem, usually a deterministic optimization problem, and then they throw in tunable parameters like finding the shortest path. Google Maps tells me this path. Turns out I have 2 decisions, not just the right path, but when to leave. And the when to leave depends on how long the trip is. Google says 40 minutes. I'm like, oh, okay, I don't know about that 40 minutes. I don't trust that. I'm going to add on 15 minutes to be safe, okay? And so that is a tunable parameter. And if I do this trip over and over again, I'll learn whether the 15 is a little bit too big or a little too small. Energy generators, the grid operators, when they plan energy generation for tomorrow, they put in buffer in case one of the generators fails. They have to, effectively by law. Now, here's an actual example of cost function approximation. Advertise the product that maximizes the estimated revenue from a product. Now, if the estimate of a revenue from a product might not be a very good estimate, I may not have a lot of noise, and maybe it's lower than it should be. And if it's lower than it should be just because of noise, I may go, oh, that looks like a terrible product. Well, actually, it's a very good product. You were unlucky. So what I'm going to do is add in a tunable parameter theta times the standard deviation of the estimate. So if I've done this many, many, many times, that standard deviation will go to 0. But let's say I haven't. Let's say I have a lot of uncertainty. What I'm going to do is say go up maybe 2 standard deviations and then do it based on that. Now, all of these, I have to tune it. So here's an example of a lookup table. I have 7 materials. I want to find out what's the best material that ends up, the best catalyst that ends up maximizing the strength of a material. So let's say I have a belief about how well each of the 7 catalysts is going to work. And let's say testing a catalyst is a very time-consuming and expensive experiment. So let's take that 7th catalyst and try it out. And the observation I get is way higher than I expected. Now, it may be that because of the relationships between these catalysts, that what I do is not only do I get a bump on the one that I did try, I can bump up almost everybody else to some varying degree because of whatever my underlying belief model is. Now, policies. Here are 3 types of policies. Upper confidence bounding. That's what I just, that's a variation of what I just showed you. You take how well you think something's going to perform, the mu bar, plus theta times that log term is an indication of how many times I've tried something. Interval estimation is the one that I described just a few slides ago. I have an estimate plus theta times the standard deviation, and something called Thompson sampling that randomly samples from my belief curve. Each one of these has a max operator, which means they're all optimized. The policy itself is an optimization problem. Each one has a tunable parameter. So let's take interval estimation. It turns out I've actually had very good luck with interval estimation. Now, let's say I take all of my 7 catalysts and I set the theta equal to 0, which means I'm going to base my choice based on what I estimate everything to be, and I'm going to come in with that 5th catalyst. Now, if I take theta equal to 2, all of a sudden, it looks like that 7th catalyst might be best. Now, what I'm going to do is tune the theta, and the graph in the lower right there, smaller is better. So this is opportunity cost. And I'm competing against a powerful and fairly complicated method called knowledge gradient. The interval estimation, which is a way simpler policy, but if properly tuned, will outperform a much more sophisticated strategy. But you have to do the tuning, and the tuning has to be done well. It is sensitive to the tuning. And this is often overlooked in the academic literature. The people who do it in practice know about this. And the tuning is hard. Here's another example of a more complicated energy problem, and I'm going to cheat a little bit on this one. I'm going to use a problem where I have to look into the future. Now, this is one where I'm looking at 24 hours, and the black line is the actual wind from history. Now, the blue line is my forecast as of midnight, and with every passing hour, I'm going to update that forecast. You can see the forecast is really changing. By the way, this is real data from PJM. Now, what I'm going to do is I'm going to do a deterministic look ahead. And in my deterministic look ahead, I have to deal with the forecast. So there I've got that forecast acting as well known as everything else. And it's not. It's not only a random forecast, it's a really pretty bad forecast. So, hey, here's one idea. I'm just going to throw in a tunable parameter. I'm going to think of it like a discount factor. So now what I've done is I parameterized my look ahead. It's still a deterministic linear program. It's still very easy to solve. But I've got to tune that theta. So now I have a parameterized deterministic optimization problem. Now I can optimize looking forward by solving a very easy linear program. It's no harder than without the tunable parameter. I make a decision now, roll forward, optimize in the future. And by the way, solving this linear program is done in an eye blink. Make a decision now, roll forward, make a decision now. Now, if I test this out on a problem where the forecasts are all perfect, lo and behold, the optimum theta should equal 1. Okay, that's what we expect. It turns out it actually is true. The best value of theta is 1 if the forecasts are perfect. But if you throw in much more realistic forecasts, all of a sudden the thetas are often moving to like much smaller than 1 and sometimes bigger than 1. So that's, I don't entirely understand that. I think that's a great area of research for somebody. Here's a problem where I'm comparing the base case is theta equal to 1, and I'm getting roughly 20 to 50% improvements. It averages out to about 30% improvement. That's a pretty good improvement. Aside from the fact that I have to do the tuning, running it in the field is no more complicated than a deterministic model. It turns out this idea of a parameterized deterministic model is very widespread in industry. Airlines put in buffer slack into their schedules. Manufacturers have buffer stocks in their inventories. Grid operators all put in, they plan for needing more energy than they really need. And you guys do it in Google Maps when you add in some buffer time to determine when you should leave on the trip. Now, tuning policies is not the easiest thing in the world because I have some nonlinear surface, but I don't know what it is. And if I pick two values of theta and do a simulation or an observation, I get something noisy. So this is not itself an easy thing to do. This is stochastic search. You have derivative-based methods and derivative-free methods. By the way, both derivative-based and derivative-free is itself a sequential decision problem. In stochastic gradient methods, the step size alpha is the decision. In the derivative-free method, finding the combination of thetas to test out is the decision. But stochastic search for the tunable parameters is a sequential decision problem. So you're facing, with the PFAs and CFAs, you're facing a sequential decision problem to solve a sequential decision problem. All right, fine. Let's move to the other class, the look-ahead approximations. Now, there's two classes of look-ahead approximations. What you're doing with a look-ahead is you're saying, okay, I've got to make this decision. Here's Dorothy from Wizard of Oz, but I have to think about the downstream effect of the immediate decision that I make now. Now, this is very cute looking at this cartoon of Dorothy and Ott, but this is the mathematical equation, and this can look quite frightening. However, here's the immediate decision of making the decision now, the immediate contribution. And then here's the downstream cost. And to be quite honest, this looks a little complicated, but we're going to have to roll up our sleeves and get around this because we absolutely need this equation. Now, if you're familiar with the decision tree, where you're at a decision node and you have to make a decision and then find the best of those decisions, after you make a decision, something random happens, okay? So when I'm back at my decision node, I have to take an expectation over those random outcomes. And then I have all that downstream stuff, which consists of making a decision, but now I don't make one decision. I have to know what decision I would make at every point in the future. And that's hard, okay? And for that, we're going to need a function. It's called a policy. Now, I call that the policy within the policy, or a look-ahead policy, because this whole look-ahead is a policy. But buried in my look-ahead policy, I have another policy, which is the rule I'm going to use in the future. The thing is, because that can be computationally expensive, I'm going to try to find something that's a little simpler to compute. Now, we'll also have to deal, so that policy will tell me what decision to make at every one of those decision nodes. And then, of course, I have all the random outcomes in the future. Now, that's really daunting, but of course, I'm going to use the power of Monte Carlo simulation. Now, these look-ahead policies, there's two broad strategies for solving it. One is to realize that a big chunk of that function, I can boil down to just a function of the state at time t+1. And that's called a value function. And this is the method that we know as Markov decision processes. Now, it turns out I generally can't compute that value function. And so what I'm going to do is use machine learning methods to approximate it. So we call that various forms of approximate dynamic programming. And there's a lot of people out there doing that. That expectation is problematic. What if X is a vector? I'm going to have a really bad day if I have to optimize over a vector value to X, and I've got an expectation buried inside my objective function. We can use something called the post-decision state that I use a lot in my work. And now I have a deterministic optimization problem. By the way, if you come from computer science, you're going to loop everything into one giant function called the Q function. That is a function of both states and actions. So here's a little example of this. Here's a grid. And we have all these random prices. More reddish means high prices, and the blue means cold, and it means very low prices. Now, let's say I have battery storage. Each of these truck trailers is really battery storage. And I'm going to have the value of energy in each one of these storage devices. Now, what we're going to do is we're going to apply an iterative learning mechanism. So I'm going to line everything up at a certain time and then simulate forward using these value functions. But then I'm going to iterate over and over again. And over the iterations, I'm going to steadily learn the value functions. Now, I'm going to exploit the fact that I know that the value function is concave, and that's going to help me dramatically. Now, over the course of the learning process, the results tend to get better and better, but not strictly. You've got humps and bumps, and this is when everything's working, okay? I've had problems where we've spent months where it didn't go up. So this can be some work. It's not always easy to do. But here's an actual grid at a particular point in time in the grid. Anything reddish means congestion. Okay, so you can see down there in the center of the grid, there's a lot of congestion happening, and tends to happen here in the Northeast, right around that area of, below Eastern Pennsylvania. This is sort of between the congested East Coast and the Midwest, where there's a lot of power generation. Now, the blue and green circles are storage devices, and in this simulation, I turned those off. I'm not allowed to use them. So you see the blue circles, but they're all turned off. In this simulation, I've turned them on using the approximate dynamic programming. And you see, and this is at the exact same point in the simulation, the exact same time, because in grids, congestion comes and goes. It's not like urban traffic systems when you can have a road be congested for a half hour, an hour. The grid moves around really quickly. So I got the exact same point in time, and you can see we've really cleared up most of the congestion, but I've got a lot of energy stored. The green storage devices, by the way, are right next to offshore wind locations. The blue are onshore, and they're close to major demand points. Now, in the world of using value functions, computer science has gotten very excited using, they call it reinforcement learning, and they're using it to help solve computer Go. Over here in my world, I like to optimize grids or fleets. Fleets of 5,000 trucks here. We're still using approximate dynamic programming. Now, that doesn't mean ADP is a panacea, and it is not. So it's a powerful tool. It's a tool in your toolbox, but just one. Now, there's a lot of problems out there. A PFA isn't going to work. You don't have an obvious idea of a CFA because a deterministic look ahead just isn't going to work. And value functions, again, value function can be really hard to estimate. I mean, when you take somebody who really likes their tool, they say, here's the hammer. They're really good at finding nails. And that was me for a bunch of years. The problem is when you go out to a real problem, it has all these twists and turns and whatnot. And what I like to say is when all else fails, and all else usually fails, we fall to the fourth class of policy, the direct look-aheads. Now, that big, ugly, messy equation that I showed you before, I have a version of it down on the slide here, you really can't solve it, or certainly not exactly. Okay, so we have to approximate. So what I'm going to do is I'm going to create a brand new model called the look-ahead model. And I'm going to use the same notation. I'm going to use states and decisions and information. I'm going to put tildes on the top. You see the tildes on the state. And every variable has two time indices. Time t, which is the point in time where I'm trying to make the decision, and t prime, which is a point in time in the future where I'm peeking forward into the future. Now I'm going to introduce a lot of approximations. I'm going to approximate the exogenous information. I'm going to simplify the policies. I'm going to limit the horizon and simplify the state variable. And I'm going to maybe simplify the decisions, or at least simplify the policy, okay? And these are all the tools in your toolbox. Now, let's say that I've been able to simplify my look-ahead model so I can solve it. So I look ahead, solve it, step forward, look ahead, solve it, step forward, look ahead, solve it. Now, it turns out all of us do this when we use Google Maps. Now, this is me. I was up in Hartford, Connecticut, working with a company, Pratt & Whitney, and I needed to find my path home to Princeton, and Google Maps at 4 p.m. says, oh, yes, there's this great path right through New York City. And I'm like, no. So this is a technique that some people like to call model predicted control. Now, MPC technically is anytime you look ahead, but a lot of people equate it with a deterministic look ahead. I'm sitting there going, you can't force me through New York City at 5 in the afternoon. I've got to do a look around. Now, there's different ways to look around. There's entire fields of research that go with names like robust optimization, stochastic programming, and yes, even approximate dynamic programming for solving the look-ahead model using one of these other fancier techniques. Now, here's the problem of planning an energy generation. I have to plan nuclear power plants a year in advance. I have to plan my steam generations a day in advance, my gas turbines maybe hour, half hour in advance. And then I've got the wind and solar that all get dynamically planned as time goes on. Oh, by the way, I do actually have one reservoir that is planned. It really runs on a schedule that's set a year in advance. Now, what I can do is when I'm planning today for tomorrow, I run a look-ahead model, and the look-ahead model will come back with a schedule of when to turn on each steam generation hour by hour tomorrow. So this is a look ahead for tomorrow, just like Google Maps. And I'm planning for tomorrow, but as I plan for the tomorrow, by the way, I am going to put in a tunable parameter that gives me some buffer. Now, one of the challenges with grid operation is you have all these crazy decisions where you're planning at different times for tomorrow, and then you have to plan at finer time steps. This is where you're planning every 15 minutes what the gas turbines will do. And so we're going to have day ahead decisions. We're going to have load curtailment notifications. We're going to have natural gas generation. And then finally, tapping spinning reserve, which is done on a second by second or maybe every 5-minute basis. And so what you end up with is a day full of lag decisions where some decisions impact forward. Now you have to move forward in time, but some of the decisions impact far in the future and some decisions much more closely. And this is a complication I don't see in the reinforcement learning community. Okay, big breath. We have just covered all 4 classes of policies. We've covered the 2 policy search classes, the PFAs and the CFAs. We've covered both the Lookahead, the VFAs, and the DLAs. I claim that these 4 classes are universal. They're meta classes. They cover every possible class of policy for making decisions. They cover whatever you're doing now. It covers whatever the company is doing now. Now you can ask, are they using the best class? First thing I would ask is, are you doing the best you can within your class? Because that's the easiest to modify. But this is very practical, and it opens the door to practical ways of solving the problems. The academic literature is full of complicated ways. The academic literature is dominated by value function approximations and stochastic lookaheads. The real world is dominated by PFAs, CFAs, and deterministic lookaheads. So please go to the website, tinyurl.com/PalJungle. Find this slide, please print it out, pin it to the side of your desk. If I ever come down to Texas A&M, I'm telling you, I will be looking for this slide. It gives you the canonical framework of how to model a problem. It illustrates all 4 classes of policies. And this is what you're already doing. Now, policies in the policy search class are the simplest. And as a result, this is what you're going to see most use in practice. But what I like to say is the price of simplicity is tunable parameters. And tuning is hard. So anytime you say, oh, I've got decisions under uncertainty and oh my gosh, stochastic optimization, you're going to find somebody out there saying, oh, no, we do something simpler. You just nod knowingly and go, yeah, you're going to be using a PFA or a CFA or a deterministic lookahead that's probably been parameterized as well, just as I did with my energy storage example, where I did a deterministic lookahead, but I threw in some tunable parameters. And that's fine. And maybe it's quite good. I don't know if it's best, whatever. Let's have somebody do their dissertation on something complicated. But tuning those parameters is hard. Go to chapter 7 of my new book. I'm going to tell you about that. It'll talk to you about parameter tuning. So here's a basic energy storage problem. I can get energy from a wind farm or the grid. The grid I'm going to call an infinite source, but at very stochastic prices. Texas knows about stochastic prices. You have to serve a demand that tends to be predictable, and maybe I've got one of Tesla's megapacks to absorb all the fluctuations. I created 5 variations of this problem and 5 policies. The first 4 were each of the 4 classes, the PFA, the CFA, the VFA, and the DLA, and the 5th one is a hybrid. So technically my deterministic lookahead with tunable parameters is a hybrid, and I made each of them work best. I tweaked and played with the data, and I knew the strengths of each of the policies. My postdoc, Stefan Meisel, I like to highlight him here because boy, did he put in a ton of time on this one, but he did a fabulous job. And this tells you, no, you can't just learn one of the policies. And by the way, that was me for many, many years. I got a whole book on approximate dynamic programming, okay? So let's go back to that problem of searching over policies. So machine learning, we had those 4 classes of 3 classes, lookup tables, parametric and non-parametric. Those are the functions that make up PFAs. Every PFA is a class of function that you might use in machine learning. In fact, if you wanted to restrict yourself to PFAs, the only difference between machine learning and policy search is machine learning needs a big data set and sequential decisions needs an underlying model. But sequential decisions has 3 more classes, each one of which is an optimization problem, a specially designed optimization problem. So the tendency that you have to do VFAs or you have to do stochastic lookahead or stochastic programming or whatnot is just wrong, okay? And I actually claim that some of these more sophisticated techniques will very possibly underperform some of the so-called simpler techniques, but you have to properly tune them. Now, I've got a new book coming out, and yes, I'm very excited. This is a major book. This is me standing on the shoulders of 40 years of research, and I finally got it finished. You can take a look at it, including downloading rough drafts of the chapters by going to tinyurl.com/RL&SO. The book should be called Sequential Decision Analytics, but I went with the more popular names. But the subtitle is A Unified Framework for Sequential Decisions. And I claim this covers all of the 15 fields. It doesn't replace the books in those 15 fields. Each of those go into more depth. But I think it's a good starter book, even though it's a substantial starter book. Now, I am working to finish a much lighter book that I first wrote as lecture notes for an undergraduate course. And this is a version of this is available on the internet. I've signed up with a publisher now publishing. I hope to have it done by May. but it will always be available on the internet for free. Now doesn't require that I give up the copyright, so this will be always available. This is a book that, other than 2 chapters, so the introduction gives a nice introduction, and other than chapter 7, every chapter uses a teach by example style. Every chapter is one application, and then it shows how to model the application, talks about modeling uncertainty, talks about the design of the policy, and that it ends with extensions because every problem can be made more complicated. So my challenge for the academics in the audience, and also for the students, because everybody has to solve sequential decision problems. So I think everybody should be taught how to solve sequential decision problems. Now, we have established fields in optimization and machine learning and simulation, and you can hire people in this field, and there's a whole pile of books in each one of these fields and people with expertise. Once you get to sequential decisions, you have the jungle, and the jungle is a mess. I'm sorry, even some of my books. I mean, I like to think I write pretty well, but every one of these books is a hammer looking for a nail. So I think that my 2 new books solve this problem. Both of them stand much more broader. They say model first, then solve. Put down the model. Don't worry about figuring out the policy. Get the modeling done, then go find a good policy. And I actually think that'll be an iterative process, because I think what you're going to find is that you're going to want to start off with a simple policy, then go make your model more realistic, then try to make the policy better, and back and forth. I have courses on my website for this at both the undergraduate level and the graduate level. So the RL and SO book, while it'll be coming out with that, it's available for pre-order on Amazon. I don't necessarily recommend pre-ordering it. And a word of caution, it's a large book. I call it a long book that reads short, because I've marked a lot of the sections with an asterisk that says, if you're reading this for the first time, skip this section. But please, I would recommend that you get the electronic version. That's where the figures will be in color, and it's just going to be a lot lighter. So I'm going to challenge Texas A&M, try to put in a course, and if at the end, you can do it at the undergrad level, following the undergrad course. For the graduate level, I would not teach this material with a lot of math. Stay away from the theorems and whatnot. Teach this to a broader audience. My grad course had grad students from 8 different departments. And so I think this can be taught to a broad audience. So this is what I'm going to push at Texas A&M. Introduce this course. Everybody will use it. You will never have a student coming back to you and saying, oh, yes, professor, I don't use those sophisticated techniques you taught us. You will be guaranteed that they will be using the ideas that you're going to be covering in this. I have a web page, tinyurl.com/SDA field, and I call this for the field of sequential decision analytics, along with the one for my new book. Please go. And if you just remember one tiny URL, it's the one at the top for tinyurl.com/SDA field. Thank you very much. I've really enjoyed this.
Thank you very much, Warren, for that very nice, insightful, and also comprehensive view of the field of decision making. I really appreciate that efforts they're putting out there. Although we understand that the kind of official lecture time is over, but we would like to leave for at least 5 minutes for any Q&A sessions that we have with the audience. And today we have a great turnout. More than 80 people are still around. Thank you all for your interest. So great job. So now it's open to Q&A. So anybody who wishes to speak, please just feel free to mute yourself and start asking your questions.
So one thing I'm going to tell the students, whether or not you have any questions now, when you get off this talk, please go to your professors and say, this is cool stuff. I might actually use this stuff. Let me put it this way. I guarantee you, you will use this stuff. Because if you're telling me that you're going to go off and work at a job where you never make decisions or help somebody make the decision, I don't care if you're a laboratory rat or you're somebody dealing with energy systems or whatever, you got to be making decisions. And new information will come in after you made the decision. You've got to deal with uncertainty. This is a universal problem. And so,
yes. So maybe I'll just start off by a quick question, which is sort of motivated by a lot of the energy-related problems. Many of the issues that we do, especially when it comes to closer to real time, is this sort of a safety and reliability kind of concerns and guarantees. So what is the kind of framework that we can think of when it comes to this type of sequential decision making that can build in some nice formulation of safety or reliability considerations?
Okay. Here, by the way, when I tend to work on these modeling problems, my first question tends to be, what's the decision? What decision are you making?
So for example, we can put in a very specific context of doing this type of real-time scheduling at the PJM, where the dispatch not only need to, satisfy the expected outcome, but also would like to make sure that under certain, reliability criteria.
Yeah, I understand. So let's talk about PJM and a grid operator. So the decisions start at the 2-second level with frequency regulation. They go to the 5-minute level where they're, basically the prices update every 5 minutes. And so they're making decisions on adjustments of capacity. They're tuning the ramping and whatnot. They've got decisions every 15 minutes, every hour. Then they have the multi-hour decisions, the daily decisions. So when you say PJM, there's a whole spectrum of decisions.
Right. So let's say we can just contextualize it in a very specific example. Let's just pick a one. Let's say 5 minutes level dispatch, right?
Okay.
Right.
So you're not turning anything off or on every 5 minutes. You're always adjusting.
You're adjusting the generation output. But then the consideration would be not only you want to adjust it in a way that you can have energy balance, but also you want to do it in a way that even if something bad really happened, for example, I lost the generator or I suddenly had a wind ramp, the system's reliability is still above or equal to certain threshold. So what is the kind of a modeling capability that we can consider those in this type of framework?
So first of all, the sequential decision problem. I can virtually guarantee you for those decisions, you're going to roughly go with the PFA. You're going to say, what do I think I need? And probably add a buffer. So that's the tunable parameter. So what you've got is a simple rule. So the every 5 minute stuff. Now, it can be that you can't turn anything on or off, but you can do ramping, which is still an optimization problem. And it could be a linear program. In linear programs, you can solve very, very quickly. But once again, it would be a linear program where you put in buffers. So that would be just like that energy storage problem. And go to PJM and they'll say, oh, yeah, we've got some buffer to handle that. Because of something random that might happen, we've got a buffer. Now, when they do the day ahead, they're very explicit. And in fact, they can be hit with huge fines if they don't satisfy what they call the N-1 constraint. They have to have enough reserve in case their biggest generator fails, okay? So their reserve, but what they do is they put in other reserves, not just one number. They have 7 regions at PJM. So each of the 7 regions, they'll have their tunable numbers because they know where their bottlenecks are within the grid. So they're every 5 minutes, probably they're not solving an linear program. They might be solving a linear program, but all but guaranteed you. By the way, I do have to tell you, you won't find parametric cost function approximation in the academic literature anywhere. That's a term I invented. I invented it watching PJM because I had all these colleagues doing these complicated stochastic programs, and then we were building a simulator to mimic PJM. And I realized that what PJM was doing was much better than what all the academics and the national labs were doing, that their tunable parameters is very powerful. What they were missing was they didn't have fancy words and a fancy name and fancy math. So if you go to tinyurl.com/CFA policy, that's a web page. You don't have to download any paper. That's a web page on the concept of a parametric cost function approximation. And where I got that idea was PJM. And I looked at what PJM was doing and I went, oh my gosh, these guys are doing it right.
Thank you. Thank you, Warren. We got another question from the audience.
Hi, Professor Powell. Okay, go ahead, Doctor.
So Warren, we also study some of the sequential decision analysis problem. I was fascinated by your talk, but our setting is more kind of in the scientific discovery type of process. And because, we kind of try to think of human scientists, how they kind of explore the space of unknown, right? In that kind of process, usually the human scientists sometimes can have a new observation is so much different from what they expect or what the existing model tell them. and they will be, so to speak, surprised. So once they are surprised, and they usually, from a human reaction, is like they need to decide, is this a kind of artifact? They better off just kind of ignore that, or they're going to just kind of treat that as genuine.
Okay.
It could possibly very dramatically change the course of action.
All right. So especially in the experimental setting. So I worked for a number of years with material scientists. Okay, and I saw all the wacky things. In fact, one of the biggest surprises is where they try out a new catalyst and it just behaves completely differently. And it turns out the laboratory assistant put in the wrong catalyst. And it ended up.
So how do you handle that kind of things in your framework?
So let me put it this way. One of the major aspects in sequential decisions is belief formation. And once you have uncertainty, it's amazing how many problems in your state variable, you have a physical state, you have other information, and you have a belief state. So the belief formation is a really major issue, especially in the experimental sciences. Okay, so you have a belief model, you get a random observation, and suddenly you're like, wait a minute, that random observation is completely inconsistent with my belief model. Well, it turns out your belief model was wrong. And one of the sources of uncertainty you have to realize is your belief model is wrong. That a belief model is not a point estimate. I used to have scientists sit with a sheet of paper and I'd say, what do you think the relationship is between your response and the density of this catalyst? And they would draw a line. And then I'd say, well, what else might it be? And that would just like, wow. And then they would start sitting on the sheet of paper, drawing a whole family of lines. Well, it could be this, and it could be this, it could be this. Scientists have a tendency to think deterministically, okay? And you have to train them to think stochastically. So imagine that you've got a relationship and you think the belief is this response, and then say, what else might it be? Draw me a set of lines where you can positively guarantee me that the outcome will fall within this set of lines. And belief formation is huge, especially in sciences. So the beautiful thing about sequential decisions for a laboratory scientist or somebody working in medicine or any of these science arenas is belief formation. And it's a really big deal. And there's a lot of these problems where it's very expensive to do an experiment. A lot of these experiments, it's not like click on an ad clicks with Google. You're talking about, I worked with one scientist where getting one experiment was a month, one whole month. The grad student had spent 2 years to get 24 data points, 2 years, without once trying to fit a statistical model, not even once. These scientists need to learn about the science of belief formation. It's a big deal. And that whole process of what did you think it'd be? And you have to train them to think with uncertainty. Don't draw one curve, draw a whole bunch of curves. Challenge them to think about what might happen.
Thank you, Warren. And let's give the last question to a student. Ali, please.
Thanks, Dr. Powell. I really appreciate that. I had a question. With this moving toward the green future and the increasing number of electric vehicles, we need more charging stations, but the infrastructure is really not there, and a lot of these charging stations are crowded at specific times. So sometimes they call this mobile storage units that can come there and help them out to answer this high demand. But each time they call this energy storage, mobile storage units, they need to pay extra money. So one decision, this sequential decision for them is that at some point they might decide to just build a new station or just buy the mobile storage by themselves. So this is kind of sequential, and we also are counting on the prediction of the future information in this sense. So I was wondering what type of framework or optimization formulation might be appropriate for considering
Great. I love this. Before you start anything, don't try to figure out how to make the decision. Model first, then solve. So model first simply says, write down your sequential decision problem. So by the way, you covered a number of decisions. You covered the decision of how to manage a mobile device. You covered the decision of where to build new stations, whatever it is. Figure out your decision, maybe multiple decisions, whatever it is. Figure out your decisions. Then write it down as a decision information, decision information, decision information. write down your metric. Tell me what your metrics are. Okay. Then once you've got your model, and every time you need to make a decision, just assume some black box will do it. Don't worry about making the decision until you build the model. Once you've built your model and you say, okay, if some black box would come in and tell me what the decision is, I can tell you how well that black box will work. Fine. Let's say you've got your model now. Okay. And that's, by the way, that's a lot of work. Now you have the issue of how to make a decision. Well, I don't know how, but there's the 4 classes. You're not going to try out all 4 classes, but think about all 4 classes. First of all, think about, is there an obvious rule? Is there a simple rule? Okay. So for example, locating a charging station, figure out where to install your next charging station. If you're greedy, you're just going to say, well, I've got one here, I got one here, the next place is in the middle. But if you look a couple steps out, you may say, wait a minute, I got one here and one here, but I don't really want one in the middle. I want 2 in between. I want to think about not just where I'll do the second station, but where I'll do the third station. Okay. I may need to look out, but start off, build the model first, assume that making the decision is some black box that somebody else will solve. Once you've got your simulator up and running, then sit down and just look at the 4 classes and say, which one feels right? And look at all 4 classes, because prior to this, without my talk, you might have been told about model predicted control or maybe dynamic programming. By the way, anybody who's heard, I assume everybody here has heard of reinforcement learning. Can anybody tell me what reinforcement learning is? Please go to my webpage, tinyurl.com/what-is-rl. tinyurl.com/what-is-rl. RL is an umbrella. Nobody knows what it is anymore. So
can you put that in the chat, please? Sorry.
Yeah, we perhaps Warren, if I don't know if you are okay with disseminating the slides. If the slides are available, then they can go and check on this tiny RL once you update your slides for this particular one. Yeah.
okay, wait a minute. So if you go to the Castle Lab website, you'll see a link for what is reinforcement learning.
Oh, you already typed. Great. Yeah, I see that.
So I typed it in the chat list. It's all of my URLs start with tinyurl.com. That's just, I put everything through tinyurl. So you just have to remember what is RL with hyphens. You know, it's very easy to remember. I don't mind making the slides available. I have a similar talk, different examples, doesn't have all the energy examples. You said that you were recording this? Because I can make the slides available, but I have to admit that the slides without me talking are kind of empty. So,
right, Warren, we are recording, and we also would like to have the slides as well, because some people sometimes they like to kind of see through the slides quickly. Right,
that's fine. I'll share the slides. I have no problem at all sharing the slides.
Appreciate that. Yeah,
I'm very into it.
Thank you. So yeah, thank you very much for all of your time and attention. I think it has been an extremely enjoyable and interactive session. I myself really enjoyed it very much. So I wish to thank Professor Warren Powell once again for his great presentation and great enthusiasm.